Good day, everyone. Welcome to our webinar, Quantum Technologies and Geospatial Intelligence. First of all, thank you to the 320 people who have registered for the event. This webinar is hosted by Geospatial Alpha, where we are building the authority in geospatial intelligence as a thought leader, as a global mentor, as an advisor, and as an investor. Thank you to our sponsors, Zapata Computing, Wilson, Sonsini, Goodrich, and Rosati, and Quantum Computing Incorporated. Thank you also to our partners, Bay Area Women in Space and Aerospace, Space in the Bay, the IEEE Geoscience and Remote Sensing Society, and the Sat News Publishing Group. I am now pleased to introduce Dr. Rupak Biswas, the Director of Exploration Technology at NASA Ames Research Center. In this role, he is in charge of planning, directing, and coordinating the technology development and operational activities of the organization that is comprised of advanced supercomputing, human systems integration, intelligent systems, and entry systems technology. He is also the manager of the NASA-wide high-end computing capability project and leads the emerging quantum computing effort for NASA. Dr. Biswas?
Thanks, Todd, for the introduction and for inviting me to speak at this event today. NASA is a mission agency focused on aeronautics, space exploration, and scientific discovery, all for the betterment of humankind. As you can see from this slide, NASA currently has 6 focus areas, and all of them have the word explore in them. As NASA astronaut Frank Borman said, exploration is really the essence of the human spirit. Let me briefly describe each of these 6 areas. We begin, of course, with aeronautics, the first A in NASA. It includes developing quieter, faster, more fuel-efficient aircraft, as well as in-time system-wide safety assurance as global airspace operations grow exponentially. It also covers assured autonomy for aviation transformation, as eventually millions of unmanned aerial vehicles, also known as drones, will be inserted into the national airspace system. The next 2 images on the top row are about human space exploration. The first in low Earth orbit, as on the International Space Station, and the second with the recently announced Artemis program to land the first woman and the next man at the south pole of the moon by 2024. Remember that exploration of the moon and Mars are intertwined. Artemis provides an opportunity to test new tools, instruments, and equipment that could be used for Mars, including human habitats, life support systems, and technologies and practices that could help us build self-sustaining outposts away from Earth. Along the bottom row, the first image represents NASA's efforts to develop new innovative technologies that enable exploration. This includes almost everything one can imagine and is often developed in partnership with the commercial sector, small businesses, academic institutions, and international entities. Also implied here is the subsequent infusion of NASA-developed technologies into more traditional consumer-oriented domains. Of course, we all know about NASA's contribution to freeze-dried food, but there are many other examples. Just Google it. The bottom middle picture highlights Earth. One very interesting aspect of NASA that may not always be obvious is that by being a space agency, we have a unique perspective of Earth that other ground-based agencies do not. Hence, we can use space-based observations and measurements to provide information not available by other means. The goal is to characterize the Earth in terms of its properties on a broad range of spatial and temporal scales to understand the naturally occurring and human-induced processes that drive them, and to improve our capability for predicting its future evolution. Finally, NASA wants to explore not just the Earth, Moon, and Mars, but the entire solar system and beyond. We are interested in two complementary facets. First, are we alone? Or more scientifically speaking, do conditions exist somewhere in the universe that could harbor life, at least in the form that we know? Some of you must have heard about the Kepler Space Telescope that discovered Earth-sized planets orbiting other stars in the habitable zone. Thus, one could reasonably expect life to exist on one or more of these planets in other star systems. The second aspect is extending life into space. That is, what would be needed for humans to live safely and work productively in space without full-time comprehensive support from Earth as we have today. To support all of these efforts, NASA conducts a significant amount of high-performance computer modeling and simulation, as well as analyze vast amounts of experimental, observational, and simulation data sets for knowledge extraction and decision-making. NASA's vast array of distributed data gathering assets on the ground, in the air, and in space collects terabytes of data each day. You might know that NASA operates some of the largest supercomputers in the world. In fact, about 15 years ago, the agency made the decision to consolidate all of its supercomputing assets under my leadership right here at Ames Research Center in Silicon Valley. However, traditional high-performance computing is not the only tool that we have. If you look at the spectrum of computing at a very coarse level, the two other computing methodologies beyond that of the von Neumann architecture are quantum and neuromorphic. Neuromorphic as in brain-inspired. At NASA, we believe that all three of these technologies are extremely attractive enablers for us to do our missions in aeronautics, exploration, and science more effectively. So moving on, we at NASA Ames have been working on quantum technologies, specifically quantum computing, for more than a decade. Today, I'll focus on quantum computing, but we also do work in quantum communications, networks, and quantum sensors. The reason we are optimistic about this truly disruptive technology is that quantum computing can assist NASA to obtain better solutions to our optimization problems. The first way that quantum computing could give us better solutions is that it gives those solutions faster than traditional supercomputers. Quantum computing might also be able to give us more precise solutions. But for both of these cases, one could argue that building a larger classical supercomputer, say with a few exaflops of computing power, could meet those objectives. Where a quantum computer really provides an advantage is that it might be able to provide a solution that cannot be found by classical methods. This slide shows some examples where quantum computing could benefit NASA. I'm not going to go over all of these, but just to highlight one or two examples is in data analysis and data fusion. As I said, NASA has lots of images of different parts of the world at different times of the year or different seasons. Each of these images give a wealth of information. But if one could combine those images and fuse the information, one might be able to get new information that is not available from any one of those single images. But this is clearly a very difficult, intractable optimization problem because you do not know what subset of the images and how many of those images you should combine to look for something that you don't even know exists. So this is clearly a problem where quantum computing could help. Another would be for, say, anomaly detection and decision making. Many times things fail, but before they fail, they give some indication that they could fail. If there was a way to track all these potential failure modes and stop the system from having a catastrophic failure before it actually failed, then that would be a great way to save a lot of remote operations. We are involved in both quantum annealing systems, such as those manufactured by D-Wave, as well as with gate model universal quantum devices pursued by Google and Rigetti. We have one of the largest D-Wave annealers at Ames with over 2,000 qubits, but we also have Space Act agreements with Google and Rigetti. Our research in quantum computing can be roughly grouped into 3 bins. First, we are developing applications that best exploit NISQ devices. NISQ devices are these noisy intermediate scale quantum devices to solve problems of interest to NASA. Second, we are trying to devise better ways to utilize these NISQ systems from a user perspective. That is, develop better algorithms, compilation techniques, debuggers, etc. Finally, we want to better understand the underlying quantum physics, such as noise characteristics, decoherence times, etc., so that we can assist hardware developers build better and more robust quantum systems, almost like the co-design efforts that have been extremely successful in traditional computing. I'm going to end here. I hope I've provided some motivation why quantum technologies could be a game changer in multiple domains. I'll be happy to take some questions, if any, at the end of the event today. Thank you for your attention, and over to you, Todd.
Thank you, Dr. Biswas. I'm now pleased to introduce Christopher Savoie, the founder and CEO of Zapata Computing. Christopher?
Thank you, Todd. So I have been given the wonderful task of trying to unpack what is a pretty provocative topic, but also pretty dense topic, which is, are we winning the quantum race with China? How do you define winning? How do you define all of these things in a very complex geopolitical situation is the topic that, but since I only have about 8 minutes to get through this, I want to caution you that this is very much a survey and very much an overview of some of the problems. And actually coming to conclusions on this would take a lot longer than this to get into it. So, but this will give you an idea of kind of where we are, hopefully, and hopefully as a conversation starter for the industry and in general. So if we look at the data that I have that's publicly available is from this Clarivate Analytics study that was done as of August 2018. I think from private sources that we have and our own intellectual property group in our company, we can confirm that the trends are pretty much the same as what you'll see here. And if anything, it's kind of continued on the trajectories that you'll see. We see that as of that time, if you did searches on the key terms in patents that are relevant to quantum technologies, and this would be quantum communications, quantum computing, and quantum sensing, the United States had a pretty clear lead in the number of patents that were applied for or issued. Here, 1,151 patents to China's 253, with Japan climbing in a close third. Next slide. But if you look at the trend lines here, in 2018, China had nearly twice as many patent filings as the United States for quantum technology overall. And we'll talk about the distribution a little bit here. But as you can see, the trend clearly tilting in China's favor as far as the number of patent applications applied for. Next slide. And if you look at it, however, from the perspective of quantum computing particularly, so not things related to communications and quantum internet, if you will, or sensing, the US does have, or did have at the time, a clear lead, and that has continued a bit. So maybe that could give some people solace that in computation, we've seen the announcements from Google and IBM and Honeywell and others who are participating on the hardware side here and have announced actual machines. And so it's maybe no surprise that in public patent filings that these companies, among others, and universities on the hardware side have taken an early lead in comparison with China on hardware and computation and algorithmic patents. Next. Next slide. However, if you look at the overall, it's not really as clear, even in computation. In the United States, you would see that there is a lead overall in patents relating to quantum computers. Again, prototypes by Google, IBM, Honeywell are currently winning in the hardware race, winning probably in air quotes for now. And then we have seen some funding initiatives like the National Quantum Initiative Act, which recently authorized $1.2 billion, and some institutes were named just a couple of weeks ago in this area. However, if you look on the Chinese side, they do lead the world in patents in communications, and there are some now billions of dollars going into research, R&D, and high-level incentives, high dollar number incentives for Chinese scientists to return home from Western labs. In addition to a large QC mega project that is in the billions of dollars, which dwarfs the amount of money that the U.S. government has put into funding in this area. Next. So where does this leave us? It really depends on your perspective. China is ahead of the U.S. in security patents and some in communications, but the U.S. Currently outpaces China, particularly in areas like superconducting patents. You see 134 to 9. However, look at the next slide. China has a significant lead in ultra-secure satellite transmission, in some areas of security, and it has doubled down on the communication side. We've had quantum communication closely tied to encryption. So depending on how you look at this, you might say that in the encryption space, decryption space, and communication space, quantum key distribution, that China has a lead in these areas that are not unrelated algorithmically and otherwise to areas that are important in even on the computational side. Next. And now China claims to be in the hardware race too. And this came out just a few weeks ago. That Pan Jianwei's team is expecting by the end of this year, by the end of 2020, to achieve a 60 qubit quantum computer at a very high fidelity rate. And the claim here from Chinese sources that it would overwhelm Google at that point if they achieve the gate fidelity levels. It wasn't clear from the article that I read whether they were talking about 2 qubit gate fidelities or single qubit gate fidelities, which is a very important difference in what their goals are there. It would make a big difference on measures like quantum volume, which is something significant to really compare systems as apples to apples. But the point here is that they've put a stake in the ground nationally to say that they are going after the hardware game as well. Next. And add to this that the FBI is now warning us of a national IP strategy. Theft is part of it, and that can't be overlooked. There is espionage happening, and we should make clear that that doesn't mean that it's all Chinese nationals doing it either. There's a lot of money going into attaining this IP at any cost, and that's something that can't be ignored. However, what should not be lost on people is that the universities and other organizations in China are quite legitimately, and through legitimately means, with the national government behind them in a very deeply coupled economy, government and industry working in tandem, going after this area, not only quantum, but other areas, but quantum definitely is specifically set forth in the 5-year plan in China by 2025 to have a lead. Next. And so why is this important? Well, you know, patents block you from practicing things for 20 years. So even if we think that this is not going to be commercially relevant for another 5 years, 7 years, pick your time frame, in the long term, in the decade-long time frame, which is relevant to a lot of corporate and government players in this area, this could lead to a huge loss. The FBI currently estimates up to $600 billion loss to foreign competitors every year from deliberate economic intelligence, but just blocking 5 years from now, 7 years from now, pick your time frame, the ability to do quantum computing because of patents that are legitimate and done through legitimate filing could be a real problem. Next. For corporations, this means that your boards really must support a journey. Usually boards are thinking about not just the next year or two, but also their entire digital transformation journey over the next 3, 5 to 8+ years. And in this case, you know, when you got a 20-year patent that just got issued this year or next year, this is deeply important and deeply concerning. So there is a message here, an underlying message that it behooves us to develop foundational IP today, prepare for derivative IP tomorrow, and secure this IP ahead of competitors, including geopolitical competitors. Next. And some example of companies that are moving there. Here's one that we've pulled out, which is Bank of America. That is very serious about this. 19 patents recently from a bank, which may be surprising to some people, mostly in security and natural language processing. But this is just to show that some companies are understanding this, looking at these things medium to longer term, and getting in this IP game. Next.
Christopher, if I can ask just a quick question.
Sure.
I wonder if there is a singular industry that might be particularly vulnerable to call it a quantum-fueled Chinese industry?
Yeah, I think that it's difficult to say that there's one particular one, but the commercial use of this technology is very broad, but areas like finance could be particularly vulnerable. And not just from a decryption attack type of a thing, but in having advantages in financial markets. And if they have patents, they're legitimate and they need to be enforced. That's the way the international patent system works. So unfortunately, legitimately, if a competitor, regardless of where they are geopolitically, has those patents, they can block you from being able to do things. And finance is an area where in trading, in things like Monte Carlo simulations and things like this, where there might be some real near-term uses of this technology that could give competitors a huge advantage. So finally, I think that is the message, that this disruption of that will be caused in areas like finance, in areas like simulation that affect the chemical industries, pharmaceutical industry, things like optimization that we'll talk about later. It's an exponential change. If you're not there, there's not a lot of catching up to do. It's kind of what we've learned in unfortunate circumstances with COVID in the last few months. Unfortunately, you know, there are 2 cases and then there are 1 million cases. And that's this kind of technology. It's exponential in the computational power, and getting ahead and getting these advantages, including the IP advantage, really is a zero-sum game in a lot of ways for the next 20 years. So it's important that we start building our workforces and securing our IP ahead of competitors, including geopolitical competitors. Thank you.
Okay, thank you, Christopher. I'm now pleased to introduce Rachele Cocks of L3Harris and Tatjana Curcic of DARPA.
Good afternoon. Thank you, Todd. So I think to start our discussion out, it's important to talk about what quantum sensors are. Quantum sensors are devices that use quantum objects, phenomena, properties to measure physical properties. Some of the quantum phenomena that you may be familiar with include superposition, entanglement, coherence, among others. So quantum sensors will be both revolutionary in replacing classical sensing technologies, as well as being incorporated into these classical systems in order to create evolutionary designs. The quantum advantage for classical sensing is the potential to integrate quantum sensing technologies into a strong base of deployable classical sensing systems that will lead to evolutionary technology transitions to full quantum sensing systems in the future. And to that end, we are evaluating evolutionary technologies that support the current classical systems, as well as quantum technologies that are truly revolutionary for sensing. So there are a number of quantum sensing technologies that are under development currently, as well as technologies that have been developed in current markets. Quantum sensing technology span a large range of sensing domains, including timing, rotation, temperature, acceleration, and gravitational measurements, magnetic fields, imaging, detection for imaging systems, electronic fields, and pressure sensing. So this wide range of quantum sensing technologies and applications make quantum sensors well positioned to move into these markets and to support current applications. Applications for quantum technologies range from medical applications, geospatial, commercial, and many others as well. So our focus today is on quantum sensors for geospatial applications. One of the key technologies in quantum sensing that it has a high maturation level as well as marketability is quantum timing. So I'm going to hand over the discussion to Tatjana Curcic from DARPA to talk more about quantum timing technology.
Thank you, Rachele. Good afternoon. It's a pleasure to speak to you today. And just a quick disclaimer, I am not representing DARPA today. All the views expressed are my personal views. And today I'd like to tell you a little bit about some exciting recent developments in the area of precision timing, as Rachele pointed out. And I'll put it in the context of GPS given the audience here. We're all familiar with GPS. It's a wonderful thing, and it works beautifully. Precision timing is a key component of GPS, and the workhorse instrument there is a cesium beam microwave clock. The GPS today is limited to about 10 nanosecond timing accuracy, and it uses RF signals that are very, very weak. So it's very easy to jam or spoof GPS. So there are a number of vulnerabilities for the system that we worry about both in the civilian and military sector. The timing technology, I mentioned cesium beam clock, is the GPS uses today is a 30-year-old technology. So today I want to tell you a little bit about what's been going on in the past 15 to 20 years in the research world, R&D world, in this area of precision timing. And the advances really present us with the tantalizing possibility that I hope to convey that in the future we might be able to upgrade GPS to timing accuracies that are orders of magnitude better from where we are today. But also because of that, we would have longer holdover times and would be able to, we would need fewer GPS updates. so we'd be able to hold the time perhaps for days versus hours today, which is again improving on some of the current vulnerabilities of GPS. So let's talk about clocks. There's been in the world of high-end atomic clocks, there's been a somewhat of a revolution in the past 20 years. Namely, we've moved from microwave clocks to optical clocks. What I mean by that is that in atomic clocks, we exploit certain atomic transitions in atoms, let's say cesium. And all the clocks that are in wide use today, we use microwave transitions, right? We can also use optical transitions, and that's relatively new, like I said, in the last 15, 20 years. And those give us a possibility of much higher precision in timing. And in fact, the best clock in the world today in Boulder, Colorado, is so precise that it would be off by a fraction of a second over the lifetime of the universe, 14 billion years or so. And that's mind-boggling. But those clocks today fill up a whole big room lab. It's a very complex apparatus. It takes multiple PhDs to run. So a challenge then is, how do we transfer some of that really amazing performance that optical clocks have to lower swap, size, weight, and power, more practical, portable, robust technologies that are fieldable. So that is a big challenge, and there are recently some developments that I don't have time to talk about today that are very encouraging in that direction. I should also point out here, given the audience here today, that that kind of precision of clocks that I mentioned earlier also gives us a resolution of gravitational redshift from elevation change of from 1 centimeter. So those clocks can resolve gravitational field at 1 centimeter difference. So that's potentially important for geodesy applications. Okay, so I talked about clocks. Let me also talk about another important ingredient in a system like GPS, and that is clock synchronization, right? So that is typically done with so-called time transfer techniques, two-way or one-way time transfer techniques, and those are today, again, in the RF or microwave domain. But recently, in the last 5 years or so, there's been a really big breakthrough, scientific breakthrough in demonstrating a two-way time transfer technique in the optical domain that has, again, mind-boggling precision, femtosecond level precision time transfer. And this was done by a NIST group in Boulder, Colorado. So here we have really significant scientific advances, both on the clock side and time transfer, clock synchronization side of things. And again, to conclude, this gives us, a potential to if we can ruggedize these technologies sufficiently and integrate them to upgrade future, GPS in the future very, very significantly and reduce its vulnerabilities as well. And of course, I'm talking, this is a long-term vision. This is not going to happen tomorrow. And I think that's all I have in the allotted time. Back to you, Rachele.
Thank you, Tatjana. So referring back to identifying quantum sensing technologies that will supersede or be significant improvements over classical technologies, as Tatjana had mentioned, gravitational sensing is key for geospatial applications. One technology that has a very high maturation, high technology readiness level for many applications is the atom interferometer. This is a technology that will support gravitational sensing. It has been developed over a number of years that now have led the technology into a point where it has been commercialized in some cases and is being developed for applications ranging from space applications, on-orbit applications, to airborne applications and ground and in between. So this is another technology that is well developed, has large potential to improve mission and application capabilities. And moving on and understanding where these technologies, where quantum sensing technologies will either be revolutionary on their own or be evolutionary with integration into classical systems, is important to continue to understand and continue to look for those revolutionary technologies and understand where their applications are going to be most impactful, especially in regards to geospatial. So moving forward, the outlook for quantum sensing, there are a number of sensors that have already been developed. Future quantum sensing landscape will cover multiple markets is the expectation. For geospatial, there's already sensing technologies, as Tatjana talked about, with quantum timing systems, quantum gravitation, sensing systems, and others as well to support those overall systems. So it's really an exciting time for understanding where these sensing technologies are going to take us. And we do see that they are going to provide both evolutionary changes as well as revolutionary changes to this market. Thank you, and back to you, Todd.
Thank you, Rachele, and thank you, Tatjana. I'm now pleased to introduce Bob Liscouski, co-founder and CEO of Quantum Computing Incorporated. Bob will lead our machine learning and climate risk investing panel. Bob?
Thank you, Todd. I appreciate the opportunity to moderate this panel. We've got some good speakers, I think, and interesting topic, a bit diverse. And we're going to be, the title is Machine Learning and Climate Risk Investing, and we're really going to look at this from a practical perspective. Our view, looking at it from a Quantum Computing Incorporated point of view, is we have a relatively short, because we're a public company, we have a short horizon in terms of trying to extract value out of quantum technologies. A lot of the things we hear about and the expectations we have for quantum capabilities, as has been characterized, will occur over several years before we realize the full quantum benefits. But there are problems today that can be addressed using some quantum technologies in the existing form, using different techniques. And I think we'll hear about some of the areas where there is some promise to extract value, particularly as it relates to climate change. In the near term, the types of things that we believe are quite apropos for quantum technologies as they relate to existing capabilities is in the optimization space, and I think you may hear more about that from one of the next panels. But optimization capabilities and looking at scheduling and demand as it relates to climate needs and trying to predict what the demand on either the grid may look like or what the opportunities may be for renewable energies, or things that lend themselves today for the existing quantum capabilities that are there. In the near term, we also see that there will be opportunity to use quantum technologies for predicting outputs or predicting climate forecasts and better weather patterns and better weather modeling. That'll have an impact and an understanding not just where we may extract value out of these technologies, but also as it may relate to Mr. McDivitt's presentation next, which is on ESG, how to better model portfolios, investment portfolios for companies that are either going to be affecting climate change or being impacted by regulations that may result from climate controls. So there's a number of ways that quantum technologies can be applied in this area. And as quantum technologies continue to progress and as the capacity for quantum computers begin to provide clear quantum advantage over classical computing, the more complex calculations that are necessary to achieve some of these outcomes will be within reach. So with that, as I indicated, we have a little bit of a diverse panel here, and I'm going to switch over to Mark McDivitt to allow him to talk about ESG and climate risk investing, and we'll start there. So Mark, over to you.
Great, thank you, Robert, and thank you everyone for joining the call today. I'd like to first share with you a brief overview, again, of the topic of ESG, and first just level set by defining the term ESG, environmental social governance. I think one of the biggest challenges, and I think my colleague Libby can attest to this, is everyone getting on the same page with actually understanding and thinking and speaking about the narrative of ESG. So I always like to say that ESG is like understanding, or in this case, learning a new language, a narrative derived from the evolution of disclosure, seeking greater transparency into the value drivers of a company by quantifying, and I always like this term, we often hear non-financial factors. I always like to say non-traditional financial factors, because as we can attest, the SASB's materiality framework often talks about those material financial factors. It's a discipline that has gained material traction globally over the past, I would argue, 18 months, and is rapidly becoming an essential tool being incorporated into standard risk management practices. I think a good analogy of this and why it's increased in importance is approximately 80% of balance sheets today are comprised of what's called an intangible asset, such as intellectual property. ESG factors are used to help better measure these 21st century assets, where investors are increasingly looking beyond standard P&L statements and digging deeper into a corporation's governance practices, employee and client engagement, as well as approaches towards environmental sustainability. So 2 words I want to draw from that definition. These are factors meant to quantify the value drivers of a company, not to be misconstrued as an effort only to force a set of values on a company. And I always use an analogy to describe that ESG is helping identify value in portfolios as a suggestion. We take 3 stocks, PG&E, Facebook, and Volkswagen, 3 very robust stocks in the portfolio, and from a financial balance sheet perspective, feeling fairly confident. We put this portfolio on, say, 5 to 10 years ago, and last week we looked at our portfolio. We hadn't looked at our portfolio for 5 or 10 years, and last week we woke up with a bit of a surprise. PG&E bankrupt. Why? Non-traditional financial factor of climate risk. E, Facebook data breach, $190 billion valuation impact. That was a data breach. S, and then of course the fraudulent software being put in Volkswagen's vehicles. I would argue that's lack of governance. That stock hit a 55% impact. Those are non-traditional financial risk factors embedded in portfolios, and that effectively drives home this idea of value drivers of ESG. Focusing on the values piece, a few statistics of note on this space. Assets dedicated to sustainable investing just last month surpassed $1 trillion. We anticipate this growth trajectory to grow exponentially over the next 2 to 3 decades as millennials, who arguably prefer and have an interest and aspiration to invest in alignment with their personal values, again, values, are poised to earn an inherent over $30 trillion over the next 2 to 3 decades. The demand for ESG-related incorporation in portfolios will increase. And then last, of course, the UN Principle for Responsible Investor signatories, representing shy of $100 trillion of assets, are committed to incorporating ESG into the risk management disciplines. So the point of this long narrative is ESG is here to stay. This is not a fad that you put in a corner. I would argue if you look at the 3 letters, the most material opportunity and arguably the easiest to quantify is the E of ESG. And if we're going to have any shot at slowing down climate change, we first need to be able to quantify environmental risks, or let's call them externalities, in these institutional investor portfolios. So I always point towards Peter Drucker's narrative. We've heard Bloomberg on stage as well saying, if we can measure it, we can, of course, manage it. So how do we do that? So I would suggest one of the challenges that, again, Libby and I have struggled with is this idea of company reported data. The challenge with that data is it's often, again, company reported synthetic or biased data. We need to go beyond that source. And I would think and point towards leveraging AI-derived technologies, and ideally focusing on and communicating with colleagues on this phone today, quantum sensors and quantum computing and how they can contribute to doing a better job in quantifying these externalities embedded in these portfolios, as well as helping build out more sophisticated climate change modeling solutions. So that in a nutshell is my definition of ESG. I'm personally focused on and committed to leveraging capital markets to help address slowing down climate change. And it starts with the ability to quantify these externalities, and would like to continue that discussion. So with that, I think this may be a good segue to pass it over to my colleague, Libby. Libby, over to you.
Great. Thank you, Mark. I'm Libby Bernick, and it's a pleasure to be here today and share with you some thoughts and insights about ESG and climate risk investing, and in particular, how there are some data challenges, as Mark alluded to, in evaluating this kind of information. So let me start by building on what Mark was describing and talk about what we mean by climate and environmental data. And what we're talking about is raw data and derived modeled data that helps investors understand and predict the financial risks or the financial implications on value, as Mark was saying, that this is about the financial implications and the value of these climate risks. And looking at this data and how it might affect a company or an investment portfolio or a loan book, for example. And when we talk about climate data, we're usually looking at data and information in two ways. The first way is around how a company might contribute to climate change. For example, does it have emissions that will make climate change worse? And the second way that we look at climate data is about how a company or an investment might be affected by climate change. For example, would a company be in an area that's more likely to be flooded because of rising sea levels as a result of climate change? So we're looking at both of those lenses around climate. And when we talk about raw data, we're really talking about linking up massive amounts of raw data about geospatial data, for example, around the Earth. So this is typically unstructured data sets that characterize the conditions on Earth. Is it an area that's being flooded? Is it an area prone to drought? Are there emissions, for example, or ambient air pollution? We're also looking at, as Mark mentioned, company activity data, which most often is reported by the company itself, so information on the business activity. And then we're also looking at investment data. How is that information linked to an equity investment or fixed income investment? So we've got those types of raw data that are then typically combined in some way through a model where we take the raw data and apply different models to understand, again, the financial implications of climate. So for example, we might have a beverage company that needs water to create its product. And if it's located in an area where water is scarce, then there could be financial implications in continuing to produce product. As another example, we might have an oil and gas company. They have hundreds, maybe thousands of wellheads that would emit methane, which is a very potent greenhouse gas. And information about the company activity could be used to optimize production. So those are just some examples of what we mean when we're talking about this climate and environmental data. And in the next minute or two, I just want to quickly share with you some of the challenges that I have experienced over the past decade in taking this climate data and applying it and putting it in a form that investors can use. One of the examples is some work done for the Water Risk Monetizer, a global tool to put a financial value on water scarcity risks to companies and investors. And one of the challenges there was finding satellite data of groundwater levels and getting that data that was a complete coverage, because typically investors like global coverage of data sets. So finding global coverage data from satellites of groundwater and then linking up that satellite data in the same time series as all of the other hydrologic models and data sets. So this is, as you can imagine, a very big computational challenge when you start thinking about all of the water basins around the world and all of the aquifers, how they're linked, and then how that contributes to a company's financial performance by not having enough water to produce its product. A second example that I've experienced where there's been real computational challenges has been linking the geospatial data, the environmental data, to a physical asset, and then to the actual owner of the asset, and then to the actual security. So if you think, for example, about a mine located in a very remote region, first you have to identify what are the geospatial characteristics around that mine, identify the mine, then find out who owns the mine, and then link up that mine to the actual security, whether it's an equity, an investable equity, or a bond. That all may sound easy, but this information changes all the time, both at the security level and the physical asset level. So if you're looking, as investors do, across a very large universe of assets and securities, then you can start to imagine what type of computational challenge this can be. And the third example I just want to share quickly is related to what I think of as an imagery challenge, where we try to assess the vulnerability of a physical asset to climate risk. So for example, if you are investing in commercial real estate and you have a large portfolio of buildings, the physical assets, we can use climate models to understand which of those assets are exposed to rising sea level, flooding risk. But then we need some way to understand what's the vulnerability of that building. Will there actually be financial material damage to the building as a result of the rising sea level? So having imagery of that entire portfolio of physical assets around the world and being able to understand how they're made, what they're made of, how they will fare in a flood helps us to understand that financial risk. And it's very difficult to get that data digitally. It is largely done by hand at this point, and you can imagine the computational challenge involved in that. So just to sum up before I turn it over to Kyle, as investors, what we're looking for is really coverage on a global scale, which creates computational challenges. We're also looking for a wide range of industry sectors, so having data that crosses multiple businesses and industries at an appropriate resolution, so detailed enough, but not overly detailed, providing some sort of quality and accuracy to support a decision that is going to be used to allocate capital. So having the conviction of the decision-making that you can rely on the data. And then, as I mentioned, making sure that that data at an asset level can be linked to the owner and then can be linked to an actual investable security are some of the challenges and opportunities that quantum computing can assist with. And I'm going to turn it over to Kyle, who's also going to share some examples that he has worked through at Descartes Lab. Kyle?
Thank you, Libby, and thank you everyone for joining this call. Building on a number of the examples that Libby has provided, at Descartes Labs, I approach environmental risk from the perspective of what new information can come from remote sensing, from satellite imagery, and from other geospatial data. On my computer vision team at Descartes Labs, we use machine learning and other techniques to automate and scale these insights to the entire globe in the way that Libby was describing. When I think about environmental risk, as Libby just described in the previous segment, I find it useful to frame the discussion in a similar way as a two-way relationship. What is the impact of a company on the environment? And then what is the impact of the environment on that company? To put a few concrete examples behind that, is a company sourcing its materials from suppliers that are cutting down forest, driving climate change? Or how much greenhouse gas is a company responsible for emitting across its scope 1, 2, and 3 emissions? Examples of the other aspect of this relationship, the impact of the environment on a company, include how vulnerable is a company's assets to extreme weather events, or to disruptions in their supply chain, or to short and long-term changes to the demand for their products driven by changes in the climate. These risks are clearly not being accounted for correctly currently, and in fact, according to Morgan Stanley, between 2016 and 2018, climate change-related weather events caused more than $630 billion in economic damage worldwide. These are inherently spatial problems. In order to quantify flood risk to homes, for example, you need to know where the homes are located, and you need to be able to predict the extent and the severity of that flooding. The domain that I work in remote sensing and machine learning, provides powerful new data to understand these climate risks. Remote sense data allows us to map infrastructure in a way that is unbiased to self-reporting, for example. I also find it useful to think about remote sensing and machine learning and the opportunities there in terms of map, monitor, and predict. Map where things are in space, monitor activities and changes in time, and predict events or risks in the future. As a concrete example, in collaboration with the Smith School at Oxford University, we've recently completed a project to map all of the large-scale solar farms in the world. Hang on. This study gives us the foundational building blocks to understand the global renewable energy system, to study trade-offs in land use, and is a critical building block for us to be able to design a system that can handle the penetration of variable renewable energy. This illustrates the big data computational challenge of these techniques. In order to perform this survey, we processed over 500 terabytes of imagery through neural net models in order to produce a data set of approximately 70,000 facilities with completeness across the entire globe. And to me, this illustrates the potential of remote sensing and machine learning to build these kinds of global complete surveys that Libby was talking about in an unbiased way and at this very large scale. Briefly, two other examples are we use satellite imagery, radar-based satellite imagery to monitor broad areas for forests being cut down, associate these with the sourcing providers for specific companies, and then give them actionable information in order to be able to prevent future deforestation activity. And finally, with respect to the risks to companies from the environment, example that we work on is processing weather satellite imagery in near real time to detect new wildfires as early as possible. To wrap up here, infrastructure maps provide a critical input to understanding the environmental impact to and of companies, and these can then be combined with accurate models of risk factors such as extreme weather events or supply chain disruptions. And this is an area where I see quantum computing as bringing potential promise, is improving these risk factor modeling. When we're trying to predict the future, we want to understand the range of possible outcomes rather than single answers. So this could be weather forecasting, flood or fire prediction, or even long-term climate change predictions themselves. So pulling these pieces all together, there is a opportunity to measure and monitor the actions of these companies on the environment and to produce improved governance and transparency for ESG metrics, as well as an opportunity to accurately quantify the environmental risk to these company assets, supply chains, and markets. I'll wrap up there and hand it back to you, Bob.
All right, Kyle, thank you. It sounds like you're getting a jump on the workforce development angle with your child in the background. So what we've heard, I think, is just a really good description of where the opportunities and the challenges are, particularly in the climate side. And then you can replicate that across a lot of other domains. But the problem space is very similar with regard to computational challenges and data. And we talk about quantum sensing, and we've already, if you think about the ability to gather and collect data today and generate data, and we consider these other opportunities for additional sensors to come into the environment, and the complexity of the variables we have in terms of trying to plug those into risk models, there's clearly here a path for quantum computing to make a contribution to these outcomes that could have a very positive result. My summary point here, because we need to go on to the next panel, is but we have to remember this is a journey. These are not going to be realized overnight. Quantum technologies today that are being developed in the hardware world are still very at their very infancy, and the types of problems we're talking about here that can be quite enormous and clearly surpass existing capabilities. But there's a clear path to getting there, and as we talked earlier on, workforce development and getting people to think about how to frame these problems that ultimately can be posed on a quantum computer is going to be where we can extract the greatest value on this. So I'm sure we're going to have more questions and answers later, but Todd, I'll kick it back to you for the next panel.
Great. Thank you, Bob, and thank you to the Climate Risk Investing panel. I'm pleased to introduce again Christopher Savoie, who will lead the Combinatorial Optimization and Distributed Vehicles panel. Christopher?
Thank you, Todd. So again, we have a limited time to unpack a pretty complex and interesting topic, especially as related to geospatial technologies and data. What we want to talk about here is combinatorial optimization and perhaps more specifically related to distributed vehicles. Now that can mean a lot of things in a lot of different contexts. What is a vehicle? Is that an automobile? Is that a drone? Is that a satellite? These are all different vehicles for different things that are quite related to different aspects of geospatial technologies, be they commercial use or dual use or military use. And we have a couple of great panelists here to kind of address these issues. And I guess we can start with Sreeja. You're in a very interesting situation in which you're at NASA and therefore working, I think, with satellites as vehicles specifically, but also with NURO, where you're dealing with other types of vehicles, and so you kind of approach these things from a geo and spatial, using that liberally, viewpoint here, and also from a small company and a governmental unit from this. Can I start? I'm going to ask each of you. I guess I'll start with you, Sreeja. What kinds of problems do you have in optimization, where in each of your roles, where you run into computational problems that just cannot be solved, or where you're running into that MP hard, if you will, brick wall, and you just can't go further without taking shortcuts? If you wanted to address that in both of your various roles.
Thanks for the great introduction, Chris. Absolutely. I work as a senior research scientist at NASA Ames and at BAERI Institute. That's the space robotics side of my life. I also lead the systems engineering team at NURO, which, as you mentioned, deals with self-driving cars, and that's the terrestrial robotics side of my life. So combinatorial optimization is fortunately and unfortunately something we deal with on both sides, because robotics in general deals with processing of perception data. Of course, the sensors that we get the data from, on which we run perception algorithms, are very different when we're in space versus on a self-driving car. but it is still a lot of data that we collect that needs to be processed. So on the space side of things, we have something called the NASA Earth Exchange, which currently sits inside NASA Ames, and Rupak, who spoke earlier this morning, has been helped supporting a lot. So what NASA Earth Exchange does is it takes sensor data from various satellites all over NASA, and it processes that information to come up with different ways in which we make sense of the Earth and its natural phenomena. So that could be things like wildfires, floods, agricultural lands, and so on. What we do with this processed data is then we task observations on the current satellites so that we can better monitor the Earth and make observations so that the understanding of the Earth improves. Now, tasking observations is no trivial task because it needs to take into consideration the limited resources of the satellites. Note that they're limited in mass and power and computational resources. So it needs to take into account these limited resources and ask them to turn on and make measurements at different parts of the Earth. It's right now almost impossible to keep all instruments on at all times, 24/7. Given these constraints. So combining and permuting which instruments need to be turned on, which spot of the Earth, depending on what's more urgent, is a pretty solid optimization task. So currently, all of this is done on the ground because it's computationally heavy, and the resultant schedules are uploaded to satellites, and the satellites just blindly follow these things. Going forward, if we want satellites to be more responsive and not be waiting for human in the loop schedules or commands, we might want to do this on board, especially in responsive remote sensing where we're trying to say track floods or track wildfires. We want satellites to have the ability to make many of these decisions on the fly. And that's hard to do because we have very limited resources on these satellites, as I mentioned. So that's one aspect of space robotics, monitoring the Earth for fast-changing transient phenomena. Another aspect is a big upcoming field is something we're calling space traffic management. And this is also something that's being led out of NASA Ames. So right now we have more than 2,000 active satellites in space and more than 20,000 pieces of debris. So that's either dead satellites or junk in space that's more than 10 centimeters big. Now, the problem with having so much debris in space is that as the number of satellites increase, these pieces of debris and even the active satellites become an environmental hazard to these new satellites. And as we know, unlike roads, having an accident in space is very hard to clean up. And so every collision is going to result in tens of thousands of new pieces of debris, and it just goes up exponentially as asset accidents increase. So one of the big projects is to understand where satellites will be in the future. What are the potential collisions that could happen where one satellite enters another satellite or a debris sphere of influence, and understanding how we can maneuver satellites out of harm's way and prevent such collisions. Now, this is no trivial task for 2,000 satellites. If we wanted to propagate, say, like 10 seconds at a time, 7 days forward, the combinatoric space is huge in terms of the number of collisions that can happen. Now, on top of this, if we add the maneuvers to prevent these collisions, there's like even 10 or 20 maneuvers options per satellites leads to an explosion of a combinatoric space. Because keep in mind that we don't just want to prevent the impending collisions, we also want these maneuvers to not cause more collisions or tertiary or secondary collisions because of going in a particular way. So STM right now is done entirely by the US Department of Defense, but over the last, say, 1 or 2 years, the baton has been moving from the DoD to the FAA, and now it's the Department of Commerce that's going to manage it. But at some point, they're going to need a ton of computational resources to understand this combinatoric space and be able to keep space efficient as well as safe in the future. Now, the third project, terrestrial robotics, just like space robotics, I feel like all of these self-driving cars now, they're ingesting a ton of data from their LiDAR, radar, thermal camera sensors, and they're doing sensor fusion. and able to identify different sensor modalities and are able to perceive the world around them pretty fast. But the problem is in very dense traffic situations, many of the times computationally the robot tends to get confused. And if we could improve onboard resources to do these optimizations, to understand how to avoid a pedestrian while not running into oncoming or cross traffic, things like that, it would be very beneficial for more efficient and safer operations of these self-driving cars. There's also off-board computing that we need to do. So all of the data that we collect, we simulate on a daily basis to understand how our algorithms are improving from day to day. And that's, again, a ton of simulation, which right now happens either on Google Cloud or AWS. And as those providers improve their computational efficiency, it sort of percolates into benefits to many of these downstream applications like self-driving and simulation for safety.
Great. Can I move to Gaurav? And you do something very interesting in agriculture, particularly with John Deere. And as I understand it, it's on the cross-fertilization between some of the AI and robotics area. Are you running into some of these brick walls with computational combinatorics and the dimensionality of the space that you have to do, and what are your challenges there, and where might there be room for better computational modalities to help you out in that regard?
Yeah, definitely. First of all, yeah, thanks, Chris and Sreeja. I'm currently working at Blue River, which is one of the startups here in the Valley and was acquired by John Deere a couple of years ago. And before that, I have a background in self-driving cars and also automating airplanes at Airbus. And as Sreeja kind of touched, so there is definitely a lot of requirement of compute and of data in self-driving vehicles. But interestingly, very similar concepts and similar requirements also apply to agriculture. So Blue River built this flagship product, which we call See and Spray. Currently, when farmers are farming, and they're spraying their crop, currently they spray the entire crop with pesticides because they don't have a way to know which crop has the weed and which crop does not. So Blue River we build this See and Spray where we put the cameras on the sprayer and we do deep learning on the edge to detect which crop has the weed. And interestingly, only 10 to 20% of the crops have weeds, and only those crops need to be sprayed. This has two very important benefits. First, our crop becomes more healthy as we are spraying less pesticide on it. And the second is it saves our customers, farmers, dollars, because pesticide costs money, and by spraying less, there is so much dollar amount that they can spend, they can save per acre by using our tech. And at Blue River, we believe this is just a start. Farming is such an interesting environment for applying artificial intelligence because it's, first of all, farming is generally in private property, so we don't have same kind of regulation that self-driving cars or flying planes have to work around. And also the environment is very different. For self-driving car, when you're trying to build a self-driving car, you can't really stop in the middle of the road. But in farming, because the environment is not as cluttered, there is so many optimization on the operation side that you can do. But now coming to the data side and the optimization side, so we collect, we like to say that we live and die by the data, and this is both on the onboard vehicle side and whatever training we are doing on the cloud. So it's we're starting things we believe we are in the beginning of this AI for agriculture revolution. But even right now, when we go out in the field, it's very typical that we might be collecting tens of terabytes of data every day. And currently, the way we train our models is like either we use like a hybrid approach, in-house cluster that we have built using several GPUs, and then also using cloud providers like AWS. But even then, we have like the bottleneck is always that when the data comes in, how fast can we train the model, and then how fast can we deploy it? And whenever we are deploying a model, again, there also we are limited by the compute that GPU can provide. That kind of sets like a very hard kind of constraints on how deep this model could be, or these are the functionalities that we could enable. So if some new technologies, including quantum computing, can enable faster computing, that's going to be a huge asset for what we're trying to do in agriculture.
Great, thank you. We're in limited time here, but I'd like to ask you to give like a 30-second take each on, when is the right timing? And I think it's different whether you're in a startup or a larger company or whether you're with government. If the time frame is 5 years until we get real commercial use, but the IP things I touched upon earlier are really a concern, when do you start investing? When do you start playing with the algorithms, playing with these real quantum machines that are emerging? What is your timeline for that, depending on where you are? If you could keep it to just about 30 seconds each, and then we can move. Let's start with Sreeja.
All right. Yeah, thanks, Chris. That's a great question. So my understanding of the past supercomputing methods to solve these combinatoric problems has been that heuristics becomes really, really important. So the ability to exploit the framework of the problem and the structure of the problem and come up with heuristics that can best capture it and then solve it is really important. So I believe if this were to extend into quantum computing, investments from the R&D perspective, I believe, should start sooner than later, so that we can understand how quantum computing resources and solutions can exploit the structure of the problems that I described, either in space robotics, in space traffic management, or in terrestrial robotics. And as we come up with a more well-defined problem and the structure evolves, I believe the quantum solutions can evolve with it. And so while commercial scale applications may be 5 to 10 years from now, I think R&D starting earlier to starting to exploit this structure would benefit from earlier investments. Great,
thank you. Gaurav, do you have a view on that?
Yeah, so I think I kind of agree with what Sreeja is saying, and I would also add that this is also like it'll depend on whether you are a bigger player or a smaller company. My understanding is that for bigger players like AWS or Google Cloud, this is already very interesting, and this is something that they should be investing in full scale R&D right now. And for smaller companies like us, I think we see ourselves as a user for this, and whenever it's ready, and definitely sooner than later, we'll definitely be interested to start looking into this and start investing our resources in to test these systems out, and how can we integrate into our pipelines.
Great, thank you very much. Well, that's all the time we have. Let's pass it. I want to thank both of you, and let's pass it back to Todd.
Great, thanks Christopher, and thank you Sreeja and Gaurav. So we're going to now open it up to questions, and we have about 10 minutes, maybe 11 or so. So I'm going to start with a question for Rupak. Rupak, this is intentionally an intentionally provocative question. Given the breadth of opportunities for high performance computing to contribute to the NASA focus areas that you mentioned and the applications that you've mentioned, from air traffic management all the way to cosmology type simulations, in your opinion, will high performance computing have a greater impact here on Earth or beyond?
That's a great question, Todd. I'm going to answer by saying that high performance computing is already having and will continue to have a huge impact everywhere. from a science perspective, like NASA, for example, is having impact when we're doing modeling and simulation, or we are doing data analysis, machine learning, AI, whether it be for applications on Earth or whether it be for space, whether it's space exploration, whether it's probes to other planets. And like we heard today, HPC is also very a common tool in finance, banking, pharmaceuticals, everywhere. So I think, it'll have an impact everywhere. Now, we can turn the question around and say, well, are we talking about putting supercomputers in space? Yes. So if you take that as the question, then clearly we are not going to have supercomputers on the moon or on Mars. And so that's where, these technologies like quantum and radiation-tolerant neuromorphic computing could become important and play a role. Because as you get further and further away from Earth, you'll have to do a lot of processing on the edge, on the sensor itself. And so what are those things going to be? And you could also change the definition of what high-performance computing is. But if you go by the classical definition, high-performance computing is a big, massive supercomputer. Well, those are not going to be flying anywhere in space. I hope that answers your question.
Yes, it did. Thank you. I'm going to actually, before I ask Christopher a question, I want to see if Tatjana wants to answer the question that was just posed about liaising with NIST. Tatjana, do you want to respond to that?
Yes, did you want to read the question?
Oh, I'm sorry. Yes, of course. Quantum supremacy has been conclusively scientifically, has not been conclusively scientifically demonstrated yet for scientific computers. Would you like to see DARPA liaise with NIST to set up an impartial benchmark based on energy input and compute time required to achieve a given result?
Mm-hmm. Yeah, thank you for the questions. Benchmarking, of course, is extremely important for characterizing the performance of current and future quantum computers and quantum processors. And we are already doing that at DARPA. I have a program that is called ONISC Optimization with Noisy Intermediate Scale Quantum Devices, where we are trying to establish whether these limited, in size and quality, noisy devices can still offer us quantum advantage specifically for combinatorial optimization problems. And a big part of that program is benchmarking against the best classical algorithms and computers. So we are doing it. It's an important question. Thank you.
Great. Thank you, Tatjana. Christopher, over to you. I guess looking out 5 years, maybe as much as 10 years, how do you see the quantum computing stack evolving over that one of those periods of time? You can select, I guess. Is there any white space or niches for startups?
Well, if you give me that time frame, and we're talking like a decade down the road, I'm very optimistic that space, the entire space, will expand. I think somewhere in the decade time frame, at least, I'm hoping that we'll get very close to at least highly error corrected quantum computers that have a sufficient enough gate depth that we can do some very interesting things. I would really think that within 10 years, given the amount of investment that government and large companies are putting into this space now, and startups like ourselves are working in this area, and academic scientists, that we're going to have some commercial usefulness in that kind of a time frame. And once that happens, just like in other technologies, then you get the later adopters coming in. It's not just the early adopters, and there's kind of a momentum that gets going. So certainly if you give me 10 years, there will not just be niche spaces and white space, there will be a lot of space. I think in the nearer term, there certainly are opportunities. In my role on the steering committee of the QEDC, part of the whole role of the QEDC is for industry and government to work together to identify some of these white spaces where there are needs, both on the hardware side and on the software or algorithmic side, to make this a real commercial reality in the nearer term. And there are certainly opportunities emerging both on the software side of the stack and in the hardware. I mean, there's a lot of really interesting and important engineering work that still has to happen, and that will continue for the time being. Certainly within the next decade. So, you know, there are a lot of areas that overlap between computing and software and sensing and all of these areas where a supply chain still needs to be developed. There's clearly no winner yet, and there are some dark horses like neutral atoms. We haven't seen a commercial neutral atom machine on the cloud yet, but that's emerging, and we're aware of certain players that are getting very close to having things that are really interesting in that space. We have ions. There are, you know, photonic computers being worked on, and many others. And each of those platforms has its own engineering challenges to scale and to reduce error, et cetera. And some of the algorithmic uses of those machines are different. So there's certainly going to be a lot of space to play here. If your question is specifically, you know, can I launch a startup in that space? That's a more difficult question. It's okay. You need to be able to convince investors that there's going to be, you know, $1 billion company at the end of the day, and that you cover a wide enough space that it's not just a niche thing, and not just a little niche widget of hardware or just a little tiny niche application in some small vertical on the software side. So that's, I think, a different question. But certainly there's going to be plenty of space to play. And I see definitely in the 5 to 10 year range, that is going to expand immensely once we hit the momentum of having actual commercial reality for applications.
Great, thank you, Christopher. I'd like to ask Mark and Libby about future products that we might see as a result of improved computing performance around climate data, and that translates maybe through the ESG category. Mark or Libby, do you want to take that?
Mark, go ahead.
So sure, Todd, thank you for that question. Really encouraged by what I've heard today, and as Libby and I have expressed, the big challenge is the quality of the data. So I would envision products that will be able to prove the provenance and veracity of that data to then give investors more confidence in optimizing, just say like just an equity portfolio, because they have more granularity, better specificity to the externalities and building that portfolio. So I would just say kind of what's out there, but make it more robust is kind of where I think we're heading with this.
And I would add to Mark's comment that in addition to really needing data of the utmost quality, we also need ESG data and climate data that's more timely. So one of the challenges with a lot of ESG data now is that, as Mark was describing in his session, this is reported by a company. But if we can get data that's real time about a company's performance or about the conditions in which the company is doing business, is it flooding, is it under drought, and have that real-time data, that would be another way that we could see future products that would solve some investor challenges.
But I would elaborate to that, the idea of stress testing and portfolio scenario analysis. I think there's an opportunity to build out there as well.
Great. Thank you, Libby. Thank you, Mark. We have about a minute left, and I'm going to throw this question to Christopher. Here it is. If the race to quantum computing dominance is a zero-sum game, is there any initiative currently available for the scientists and businesses to work with the Chinese counterparts?
I don't believe in zero-sum games, and I personally, this is my personal opinion, you know, I've worked a lot in China and worked a lot with Chinese colleagues, and my hope is that we will find a detente in this whole geopolitical quagmire that we find ourselves in. That's my hope for humanity. I think in the long term, it behooves both of these giants, economically, politically, otherwise, to learn to get together and help humanity. That's in everyone's best interest. How do we do that with these very different ideas? That's probably a topic for another day. But if the patent area is a zero-sum game, that does make it difficult. And if we're thinking about decoupling, that makes it even harder. I think, either way, it is a zero-sum game, intellectual property-wise, even domestically. So I would say, get involved early, grow a workforce early, and start collecting the knowledge you need institutionally to be able to take advantage of these systems once they come on. Because if you wait until that magical fault-tolerant computer shows up 5 years, 10 years, whatever time from now, and then start, okay, let's go use this thing, you're going to be behind already, because you won't have the algorithms, you won't have the intellectual property portfolio to even start to think about computing. And that's true geopolitically, but it's also true domestically. So I don't think the analysis changes that much. It just gives greater urgency that there are geopolitical frenemies, friends, allies, enemies, whatever way you want to characterize it, who are also going after the same limited bucket of IP that's going to affect your industry.
Great, thank you, Christopher. Well, that's all the time we have for today. I'd like to thank our speakers today. Also, again, thank our sponsors and partners. Good evening, everyone.